Today we'll be looking at the topic of LoRa fine-tuning. It's one of my favorite topics, and this is one of the methodologies you can say that's very much prevalent in the industry to fine-tune LLMs for business applications. So if you have really specific domain adaptation you want to do, then LoRa fine-tuning is a good way to do that. So a few things on logistics. A few things on logistics. So we'll be looking at mini project 3 getting released tonight, hopefully, or tomorrow morning, and you will have about 2.5 weeks for the due date, right? So you'll have sufficient time for mini project 3. And then you have final presentations, which is on March, I don't know, is it 16th and 18th, or is it 14th and 16th? Like the finals week, so Monday and Wednesday. So we have a different room reserved for the 2 days, not this one. And so we'll have a sign-up sheet for you guys to team up and present. So there we can't do individual presentations. So if you have done individual projects, you may want to pair up with someone else. Because we have very limited slots. We only have 2 days to cover everyone. So if you're not paired up, you'll have to pair up with someone else and share the credit for the final presentation there. Okay. Any other questions on logistics? Yeah.
Is that sign-up sheet posted yet?
Is the sign-up sheet posted or not?
It should be the same one.
For the final presentation?
Oh, no, it hasn't been posted.
With the caveat that people have, people who haven't paired up also pair up.
Sure.
Yeah, so we'll do that. Anything else? Okay. Yeah, also we have a class tomorrow evening on Zoom, and we have a class on Wednesday in person. So that's 3 classes this week. And yeah, so today's LoRa fine-tuning. The remaining classes will be, so the next set of classes will be on agents, and your mini project 3 is on agents, and agents to solve really complex queries. You can say like, hey, can you give me some travel destinations that are warm, within a 2-hour flight, less than $300, also has some concert going on, and etc., etc. So you can ask really complex queries, and it pulls from different data sources and gathers the data, understands, iterates, loops through, and then generates a response. So you'll get to work with a single agent, multi-agent. So we'll look at all of that in the next set of classes. Once we're finished with that, we still have time left. We'll cover all any miscellaneous topics. So agents is like the last main topic we'll cover in this course, but that's a that's like one of the hottest topics in the market right now is agents, agentic AI, agentic workflows, so we'll kind of spend quite a bit of time on that. I think last time we taught this course, we had multimodal learning and looking at stable diffusion and working with those, but I felt this time because of where the trend is, it's good if we spend more time on agents, and you can always learn more on multimodal learning on your own. Or other topics that you're interested in. Okay, cool. So let's look at LoRa fine-tuning. I think we had a couple of papers presented related to LoRa, but we'll go a little bit more in depth. Is Hoffe here somewhere? Hoffe? Oh, you're there. Okay. So Hoffe, the in-class is set up, right? Huh? Oh, you're setting it up now. Okay, so we'll probably have a few minutes for you to set it up. Great, thanks. So, so today we'll look at LLMs, a little bit of summary of how we use LLMs, which you guys are already familiar with, and then focus more on LoRa fine-tuning. So we've been looking at mostly encoders. We also have like decoder LLMs. We'll spend some time on that as well. So typically, if you want to work with decoder LLMs, then we say, okay, you want to do in-context learning, zero shot, few shot, chain of thought, we've gone through those. Or you want to do RAG, we went through that in a mini project. So you retrieve and then you augment and you generate. The other one, which we'll cover today, is LoRa fine-tuning. This is just like, we looked at sentence BERT and the Siamese structure then, and then we also added a last layer for prediction, right? And then we fine-tune the whole model there. So that's how we fine-tuned an encoder model, is you already have like a pre-trained model, but you added a couple of layers and you fine-tune. LoRa is like kind of an analogous for that, except instead of just fine-tuning the last layer, we actually introduce a completely new layer, right? And we'll look into that, how that's done, but with much fewer weights, right? So it's very efficient. LoRa belongs to the class of models called PEFT, parameter efficient fine-tuning, where the number of parameters that are actually fine-tuned is much less than the base model, right? So much less. And we'll look into some of that as well. So just to recap, in-context learning is useful when all the context needed by the LLM to respond to a query can fit into the context window of the LLM. Is it too bright here? Are you guys able to see the screen? It's good? Okay. Yeah. So in-context learning, all the context can fit into the context window of the LLM, and you're able to get good results. These days, the context window is pretty big, so you can fit a lot of information. Doesn't mean you'll get amazing performance with very large context. The performance can start diminishing. And then we have retrieval augmented generation, where you simply cannot fit a lot of material in context, or you just want to be more performant, more accurate. And so then you use a RAG. And then we have the LoRa fine-tuned model. So this is when we need to domain adapt an LLM for a specific task. So yeah, you start with a base large language model like Llama 3 or Mixtral or Quen or any one of the models. Typically open models. We don't start with proprietary models because we don't have the weights for those to fine-tune. So you wouldn't start with a GPT, for example, for LoRa fine-tuning. I don't know what the structure looks like. I don't know what the weights are. I wouldn't be able to start with Claude for the same reason, right? But I can actually look at Llama, I can look at other open models, and then I can say I want to work with these and fine-tune them for domain-specific examples. And if you have a smaller LLM that you're fine-tuning, then it can also lead to lower latency. But hopefully you have a good trade-off between lower latency and accuracy, because if you really go small, then the accuracy starts to suffer. So you have to find that trade-off of it's not too small, it's not too large, it's not too expensive, right? And you can get that good trade-off between latency and performance, right? Okay, so let's look at the Llama model, Llama herd. So Llama 3 is one of the very popular decoder models. Come in 405 billion, 70 billion, 8 billion, 1 billion versions, also 3 billion version. And there's also Llama Guard, which is for input-output safety, to understand how safe inputs are. So there's also that variation there. So this is a little bit of information on Llama 3 herd of models. Like we do have Llama 4, but people use Llama 3 more because 4 is not as performant as 3, even though it's the more recent one. Yeah, so they've been released at different dates, and then you can see the ones that are tagged with instruct are instruct fine-tuned. So they're already ready for instructions. They already understand how to take instructions. So typically, if you are designing, you're doing fine-tuning of a Llama 3 model, and you're passing in instructions, but you want to domain adapt, you may want to start with the instruct model instead of like just a supervised fine-tuned model, right? Because it is able to handle instructions better. Yeah, and people typically fine-tune an 8 billion model or a 3 billion or a 1 billion model. So, and you can get good performance for specific tasks. Funnily, you can use these decoder models for encoder style tasks like classification, which typically we've been using BERT for. You can also use them with decoders and they work very well. Okay, so that's a little bit about Llama 3. And the more recent Llama 3 models, as you can see, support long context, the 128K tokens or more. And some of them support tool uses, some of them don't. So for agents, we want models that have the support with tool uses, right? So you can write up tool schemas and say, this is a tool schema for my tool. And when I issue a query, then use any of these tools and then gather information, and then we iterate through it and then decide what to do next. So tool use becomes important when we have agentic framework or want to encapsulate LLMs into agents. Okay. A little bit about the architecture. So we looked at encoder architecture in a lot of detail. The decoder architecture is not too different, except that the self-attention is kind of a masked self-attention, where you only see tokens until the past, but not in the future. Like if you look at BERT, it's bidirectional encoding transformer, so you see both ways. But with decoder, because you're actually generating one token at a time, you don't want to train in a way that you see the future, because when you actually predict, you don't see the future either. So why do you want to train in a way that you see the future? So that's masked self-attention. So that's the thing that's different between encoders and decoders. Self-attention, right? Most of the other components are similar. Maybe there's a little bit of activation functions that are different. The way the normalization happens is different, but kind of the layering and multi-head attention, all of that is pretty much very similar. The loss function is also different. We use masked language modeling with encoders. We use next token prediction as the main loss function, because you're auto-regressive. You're trying to predict the next token. You're trying to generate the next word. So the loss function also is more geared towards next token prediction. Okay. Okay, so LoRa fine-tuning refers to, LoRa stands for low rank adaptation of large language models. It refers to an efficient fine-tuning procedure where all weights of the LLM are frozen, but new and relatively fewer weights are introduced for fine-tuning, right? So this is a graph taken directly from the original paper on LoRa. So on the left, you see the blue square. That's the pre-trained weights. They've already been trained, fine-tuned. Let's say it's instruction fine-tune or supervised fine-tune. They already exist. On the right are the orange set of weights that you're fine-tuning for your specific task. So I have a business use case. I want to do some decoder-based predictions, and I want to fine-tune a small language model. I would be introducing these orange weights and say, I'll freeze the blue. I only fine-tune on the orange, right? And it's low rank because you can see the orange weights are a multiplication of A and B. So the two boxes on the right, you multiply them and you get the new weights that you're generating. So they're parameterized in a low rank fashion. And because they're parameterized in a low rank fashion, the effective number of weights is much less than the original set of weights, right? So the dimension of the product of A and B is still D by D, right? If you multiply a D by R matrix with a R by D matrix, what do you get? You get a D by D matrix, which is the same dimensions as the one on the left, except the number of parameters on the right is much fewer if R is much smaller. So depending on the size of R, you can have a much lower parameterization for a D by D matrix. So that's where the low rank comes into play, is keeping it efficient. So parameter efficient. So the efficiency is coming from the low rank component, right? Like this is very much reminiscent of matrix factorization. If you've seen some matrix factorization models in the past, SVD, eigenvalue decomposition, Collaborative filtering, recommender systems, some of the things they used was like simple, started off with a bilinear matrix factorization model. So, but here, no, we're not doing recommendations. It's a very generic model, but we're parameterizing the weights in a low rank fashion in a matrix factorization sense, right? Okay, so we'll look at in-class exercise. So hopefully it's set up. It's set up. Okay, halfway's done it. So let's take like maybe 30 seconds. Take a look at this question and you can put in your response for the in-class exercise. Okay, the next thing we'll look at is, the basis for fine-tuning in this particular way is the assumption that the learned weight matrices in LLMs typically reside in low dimensional subspaces. So people have anyway found out that when you train LLMs, the subspace in which it resides is anyway a low dimensional one. So you might as well learn a low rank matrix for fine-tuning purposes. It wouldn't be too much off track, right? It wouldn't be too much off accuracy. So that's kind of the basis for using a low rank factorization here. And yeah, so one thing I forgot to mention here is like once you learn the orange matrix, the blue already exists from your base model. You combine them by just adding the two, right? So if you had W here, there's some scaling factor that we'll talk about, but essentially you're adding W plus A times B as your new learned weight matrix post fine tuning. So you don't discard the W. The W is also not fine tuned. The W is frozen, but you add to it A times B. Right? Okay, let's look at another in-class exercise. Okay, one thing I should mention here is that typically, with respect to what weight matrices we want to fine tune, people have found that focusing more on the attention gives you the most gain for fine tuning as compared to feed forward. Also, feed forward weights are higher dimensions, so you actually incur more parameters from there. Also, the gains, 80 to 90% of the gains from fine tuning come from attention, because the domain adaptation happens in how the attention changes in that domain. So if you want to fine tune, you might want to fine tune more for attention, is what research has shown, right? People still fine tune for feed forward, but much less these days, right? Most of the focus is on attention. Okay, so keeping that in mind, you can look at this in-class exercise and take 30 seconds. So a little bit more on the fine tuning, right? LoRa can be used to fine tune any LLM model. It's like not specific to Llama 3. It can be any LLM model where the weights are exposed or something that you can observe by freezing the entire model, and only the new low rank weights are fine tuned. And like we said, the final model is the existing weights plus the LoRa adapter weights. So typically the terminology used is base model, adapter model. And then you might also hear multi-LoRa. So multi-LoRa is where you have one base model and multiple adapters. And like if you have a modern GPU like H100, it can typically fit like one base model of 8 billion and maybe up to 20 or 30 adapters of lower memory. So you can actually fit equivalent of 20 to 30 models on one H100 GPU, because the adapters themselves don't take much space, but the base model does. So we'll look at an example of the specifics of that in one of the in-class exercise. So that's kind of like, it also, you can also do multi-LoRa, and you can do a bunch of fine tuning and host it all on the same GPU because of this low memory footprint that adapters have. Yeah. So latency is mostly same as the inference time per adapter. Um, and typically at inference time, what you do is you add the base model's weight matrix to the adapters and then you inference, because then it's just the one set of weights. So when you do it in that way, it's not extra uh, latency, right? And this is orthogonal to partial freezing and fine tuning. In Vision, for example, you can partially freeze a few layers, and then maybe the first set of layers are frozen in a CNN model, and then you fine tune the last set of layers. So this is orthogonal to that, where you actually freeze the whole thing, but you introduce a new set of parallel weights that you fine tune. And in some sense, every single parameter in the attention layers in the attention matrix of every single layer is fine tuned here. So you can fine tune all the way from the beginning to the end. And you can also select feed forward if you want to get a little bit more performance. But that's kind of an orthogonal paradigm to partial freezing followed by fine tuning the last layers. As an example, for GPT-3 175 billion, choosing an appropriate rank, you can reduce the RAM requirement for loading the model from almost like 1.2 terabytes to 350 GB. And if you use a rank of 4, the checkpoint size of a fine-tuned model can reduce from 350 GB to just 35 MB, right? Because you only have to checkpoint the adapter. You have the base model stored, but the adapters themselves don't have a lot of physical memory footprint, right?
So why do we need a base model like this? Why isn't just a whole bunch of adapters sufficient to just replicate the whole?
Oh, the adapters are on top of a base model. That's
no,
how.
I hear you, but
Yeah,
I'm is why have a base model? Why don't you just have a whole bunch of adapters and just train?
Because you want to have shared learning. This is the idea of multitask learning. Like you the base model has a lot of scope. The adapter has a very narrow scope, but it derives some of its scope from the base model. So you adjust the scope of a base model with an adapter. It's saying put an adapter in, suddenly the scope changes, but in a specific narrow way so that I can address a specific task. So I don't want to train a whole new adapter with a full set of weights for a specific model. When I imagine like you are working.
I'm suggesting the reverse, right? Which is even the base model
Mm-hmm.
could be.
You're talking about a small language model.
Yeah, or a base model could also just be consisting of a bunch of.
Low rank matrices.
Yeah.
Yeah, there is like multi-head latent attention, so where they do a low rank factorization of the attention matrix itself in the training of the base model. So that's a paper by DeepSeek. They incorporated multi-head latent attention and also mixture of experts. So you can do that, but that's a good suggestion. But I would argue even there, the footprint of that base model is still pretty high. You would still want to add adapters on top of it for domains, specific domains. You had a thought?
Yeah, I was just going to ask for the low rank adaptation assumption. It says that like weight matrices reside in like low dimensional subspaces. How true is that? Because there's that paper I think from like last year where Stanford found that for like llama or SU, like a lot of the LLM models that people use, you could get like verbatim recall of training data. For example, like Harry Potter and the Sorcerer's Stone, like other literary works, like they give a sentence and they're like, repeat this, like finish this like story verbatim, and it would just give it like verbatim. So kind of like is that relatable where it's like, okay, it's overfitting or maybe like memorizing training data for certain tasks, and that's maybe not great because then it gives like access to data that users should not be able to get access to.
Mm-hmm. So what's your question?
So my question is like how true is that assumption for like just general purpose like LLMs? Like how true is it that like the weight matrices reside in like low
Yeah. So there is, yeah, we'll go through some results where there's a blog post from thinking machines called LoRa without regret. So they actually compare. So LoRa, when you actually increase a rank to full rank, that's as good as a full fine tuning. Okay, so they compare full fine tuning with ranks that vary from like really tiny ranks like rank 8 to like 128, 256, and we'll see some results on that. But there you can see like the gap between a full fine-tuned model and like a low rank fine-tuned model, and where does the accuracy start to diminish, right? As you increase the rank, the accuracy does go up, but there's diminishing returns. So that is an approximate way of understanding that you don't need like a very large rank for super good accuracy. So we'll look into that. But I think memorization is a completely different topic. So maybe we'll look into that a little bit later. You have any thoughts, Arnav?
Yeah, I think the assumption for low dimensional subspaces is that like if you're tuning something towards a very specific domain, then the updates with respect to that domain are in some low dimensional subspace, but generally during pre-training and like the initial stages of post-training, you're sort of aimed towards training a generalist model. So in those settings, maybe it's not true that the updates are usually in that low dimensional subspace. Which also sort of relates to what you had asked earlier, because you usually want to have like as general of a model as possible before you do any sort of low rank stuff. So it makes sense to sort of over parameterize your model and then later during post training do the low rank stuff instead of trying to have everything factorized from the get go, because then you can limit how flexible your model is.
Yeah. Yeah, I think that's a good point there. I think the multi-latent attention is a paper where they actually parameterize in the base model itself, but it's not like rank 8 or rank, it's not like super low rank. So we are actually talking about very low rank parameterization. You can still do that, but to some extent. So you might have 256 or 512 or a little bit higher ranks in the base model parameterization. And we'll look at a graph that kind of compares that for full fine tuning versus parameterized fine tuning. Okay, cool. All right, so that brings us to IC3. Let's take a look at this. So let W be a D by D dimensional matrix that can be thought of as a product of A and B. And let's say we have a token embedding X of a token T that lives in D dimensions. And W, let's say the W represents a query matrix. The question is, what is the cost of computing the query vector from this weight matrix for the query? So the query vector is obtained by multiplying the weight matrix for the query with the embedding, token embedding. So okay, so we have one more. Okay, so one more in-class exercise. This is interesting, a little bit more involved. Assume the embedding dimension is 4,000. So, and let's say we did LoRa fine-tuning with a rank of k equals 5, so much smaller than D, which is 4,000. So if the LLM model we're fine-tuning is a 8 billion Llama 3 model, how many new parameters are we introducing with the fine-tuning? Okay. So essentially, you have to start with 8 billion and say, how much am I downsizing from 8 billion? What's that factor? So divide 8 billion by that factor, and you get the new set of parameters and their dimension. So the way to do it is to compare A with W and B with W, because you're essentially looking at how many fewer parameters are there in A and how many fewer parameters are there in B and by what factor. And then you get the net factor reduction, and then you use that to divide 8 billion by, and you get your answer. Okay, what's your answer? 40 million. What else? Any other answers? This is assuming we parameterize every single weight matrix in every single layer. Okay, any other? So look at the W matrix, right? That's 4000 by 4000, and look at the A matrix. That's 4000 by 5. What's the factor here in terms of reduction between W and A? What's the factor? Like when you divide the number of parameters in W by this factor, you get the number of parameters in A. What's that factor?
One number would be 60 million, the other would be 20,000, right?
Yeah, so you're reducing it by, so 4000 by 5, which is 800, right? Yeah. And then you also are doing the same with B, right? So you've introduced a few more parameters. So now the factor reduces from 800 to 400, right? Because you have an extra set of weights, which are the same. So you divide 8 billion by 400, and you get 20 million. So essentially, if we have a low rank of 5, we're taking an 8 billion base model and only adding 20 million new parameters, okay, for fine tuning. So that's how the memory footprint of the adapter is much smaller when you use a lower rank. Okay. Cool. So you can do the math if you're not sure and see that that's the case. All right, so let's go to the next. Yeah, we already covered partial freezing. Let me see if we want to do this in-class exercise. Yeah, I think I'll skip this for now. Okay, let's look at a few more practical considerations, right? So when we actually deploy LLMs in the wild, let's say you did a LoRa fine-tuning model. There are a few factors that we want to look at for deployment, right? One is the cost. What's the cost of deployment? Second is latency. Cost can include like how many requests am I taking, and mainly like if you're having a open LLM, what's the cost of hosting the GPU? What's the cost of serving these requests with the GPU? So essentially you have a H100 or H200 GPU running 24/7. What's the cost of that? So that's the cost. There can be other fixed costs that you have. You can add that all up. Then you have latency. How much time does it take to serve requests? Let's say you have 1 million requests a day. What's the P95 latency for 1 million requests using an 8 billion LoRa model, right? 8 billion base model and a 20 million adapter. Then you have accuracy. How accurate is your fine-tuned model as compared to, let's say, GPT or a large language model? And then you have privacy and complexity. So there are a few other considerations for deployment. Let's say we had a 8 billion Llama 3 model. So if you do the conversion of one parameter, one parameter is one float, so that's we are looking at 32 gigs of RAM, right, for a billion models. So if you want to have this in memory, you're basically consuming 32 GB of RAM right away with a base model. And a LoRa adapter that, let's say we did a rank 5, 20 million parameters, we're looking at 80 megabytes of RAM, so much less RAM. But that's how you can pack in one base model with a bunch of adapters, because they only take up 80 megabytes of memory each, right? So let's say I want to build a topic identifier by category. So this is how you want to use different LoRa models for different. Why do we have multiple LoRa models? Because you might have different categories and you have tasks associated with different categories. Let's say I want to identify a different set of topics for every single category. If I have 15 categories, I'm looking at 32 plus 15 times 80, which is 34 gigabytes of RAM. So I only increase the RAM consumption by 2 gigabytes when I go from a base model to a base model plus 15 adapters. Okay. All right. So when you do multi-LoRa, you typically say you have a H100 or H200 GPU. The base model is the same. We just change the adapters. So that's a little bit about why this is super easy to host with one GPU or a couple of GPUs. So the costing, latency, hosting, scaling, there's a lot of benefits to having adapters, and you can solve multiple problems with adapters, right, in one GPU. Let's look at LoRa versus full fine-tuning. I think there was a question on how LoRa compares with full fine-tuning. So this is connected to the technical article on LoRa without regret. So the hyperparameters for LoRa, right? If you look at how the weight matrix from the base model gets combined to form the new weight matrix, we're taking, let's say, W prime is the base weight matrix. We have a scaling factor alpha, that's a hyperparameter. We scale it down by R, the rank that's being used for the LoRa, and then multiplied by A times B. So we already know A times B is something we want to do, but we just scale it by alpha divided by R, where R is the rank that's being used for the LoRa adapter, and then you get the new weight matrix. So alpha and R are two hyperparameters. Then we also have the learning rate. So learning rate comes into play when we take a gradient of the loss function with respect to W, and then we multiply the negative of the gradient with the learning rate, and then we make a update. And then we have batch size. How much of data do you pass per batch? And so is it a small batch, a large batch? So these are a few things that this paper did a study on, and some interesting results here. So if you look at these graphs, they have multiple curves in each of the graph, and each curve corresponds to a specific rank. So rank 1 all the way to full rank. So full rank LoRa is equivalent to full fine-tuning, assuming there's no low rank. You just fully fine-tune the whole model, right? So that's the orange one. And then phi-12 is the next biggest rank, which is still significantly smaller than the embedding dimension, right? And then you have 256, 128, and so on. So if you look at the graphs on different data sets, There are 4 different data sets here, or 2 different data sets, sorry, 2 different data sets. You see that the orange graph is pretty much close to the ranks of 512, 256, and 128. The gap starts to widen as the ranks reduce, right? So the loss is actually pretty much similar when you have, yeah, it's not low rank, but it's not full rank either. So at 256 and 512, you're seeing similar performance on the test loss as compared to a full fine tuning. So that kind of shows that there is some truth to the weight matrices residing in low dimensional subspaces as far as the test loss is concerned and accuracy is concerned. Right? This is a graph that looks at how the final loss for the test set compares with the learning rate for different ranks. So obviously the learning rate, certain learning rates are better than others. And there's a range in which they're reasonable. So you can see though that for the full fine tuning, the learning rate is actually maybe 10 times smaller than for the LoRa models. But they have a similar profile of where they dip on the loss and where they start to go up. So that's kind of similar. So yeah, I mean, you can use these graphs from different data sets to also pick a learning rate. You say, okay, how do I pick a learning rate? You can also look at this paper and say, I have a good starting point for my LoRa model. You can also do hyperparameter tuning and pick a better learning rate as well. So this is one on batch size. So you can see it's a combination of rank and batch size. So the red one is a full fine tuning with 32 batch. And then we also have, let me just see here. Yeah, so full rank and then a 128 batch. Yeah, as the number of examples increase, so the more the number of examples, the more the gap between a full fine tuning and a low rank fine tuning, right? So the gap starts to widen only a little bit later. If we look at a batch size of 32, and then you compare the full versus 128 rank, there's not so much of a gap. So this kind of says that maybe there is an optimal batch size and that's not too big. Maybe a batch size of 32 data points at a time is actually preferred as compared to a larger batch size. And there is less of a gap in the curves between a low rank model and a fully fine-tuned model as well. And this is a graph that says which ones do you want to use, like the multi-layer perceptron, attention. You want to use everything for as far as like the loss is concerned. So okay, this is counterintuitive. It says attention only LoRa underperforms multi-layer perceptron only LoRa and does not improve performance. Huh.
What is the loss function?
The loss function, this is, I think, this is probably the next token prediction. So it's basically the cross entropy loss, so that we're looking at. It's a little bit counterintuitive. It says attention only LoRa significantly underperforms MLP only LoRa. Huh. That's interesting. The red graph is actually above the others. So it's saying that if you use only attention only LoRa, that's actually underperforming. Okay, we need to look into this a bit more. And if you use everything, MLP and attention, then there's not much of a difference. Yeah, so the gap is only between the red curve and the rest. The other curves are pretty much similar. But is this also with a higher rank? Is that why? We have a high rank here, 256. Okay, so we're also in a high rank regime. We're not at a low rank regime. So these graphs are for a different set of ranks. Interesting. And also there is a dense full fine tune. So that is, you don't actually low rank parameterize, and the performance is similar to, let's say, a 256 rank fine tuning. So that kind of tells you that, from all of these graphs, you see that there is diminishing returns and increasing the rank. And at some point, you're not too far away from a fully fine-tuned model. So full fine-tuning is pretty close to like a 256 rank fine-tuning is one of the takeaways, right? But again, this depends on the data set and depends on the task that we are looking at. For simpler tasks, like if you're having a lot of like classification-based tasks that you use a decoder for, that's even simpler. You can get away with much lower ranks for better accuracy. Okay, cool. Right, let's look at, so summary of the results from this paper, right? Higher is better, but you have diminishing returns. And lower is better for batch size. So 32 was found to be optimal. And the learning rate for LoRa models is 10x of what you find for a fully fine-tuned model. And the scaling factor alpha is around 32, seems to be optimal. So overall takeaway from this is that LoRa is not just an adapter, because you'll say, oh, LoRa is an adapter, okay, that's doing something. But if you actually scale the rank, it can come close to performance of a fully fine-tuned model as well, where you fine-tune every single weight on certain data sets. Okay, so here's one result which I looked at for different intents related to, let's say you have a buyer-seller interaction, and then you have different intents on the kind of questions that are coming in, like the relevant intents are item condition, item availability, item aspects. The irrelevant intents are in the beginning, like irrelevant intent, prompt injection, offensive intent, price negotiation. I think we looked at some of this maybe in one of the assignments, maybe. I think the previous one, mini project 2, we had some of these, right? So what you can see is, like, this is from a little bit, maybe 1 year old result that I ran numbers on. The last column, you can see that GPT-4o has pretty good accuracy, but it also has many more parameters. Like it's kind of the model that has the largest number of parameters. But if you look at Llama 3 8 billion, which is instruction fine-tune already, it's already instruction fine-tune, not LoRa fine-tune, but instruction fine-tune. The instruct version, that has an accuracy of 82, so not too far away. But then you go from there to the first row, you look at Llama 3 1 billion, you can see the accuracy, overall accuracy drops pretty significantly, like it's at 36. But then you take the Llama 3 1 billion and actually LoRa fine-tune it for the specific task. It jumps from 36 to 88, right? So that's where you can see that, a fine-tuned 1 billion model can come close to a performance of an unfine-tuned larger model like an 8 billion model or even GPT-4o. So that shows you the impact of actually LoRa fine-tuning on specific domains. So this is for this specific domain, not for other domains where this might actually not perform so well. Okay. And then you can also see each column shows you the accuracy on that specific intent. Some of the intents are, like, I think Llama 3 1 billion, like it does well on item aspects, but it fails on some of the other ones. So it's interesting. Okay, cool. Let me just see what's the time here. We have 5:40. Okay, let's take a 5-minute break, and then we'll come back for a 20-minute coding exercise. Okay, so we'll come back. So what we'll do now, maybe in the next 20 minutes, is you guys can get started on an in-class coding exercise. We don't have any assignment or mini project on LoRa fine-tuning, but this will be your exercise that you can do. We'll have it due maybe end of tomorrow, so you have some time, because you have to, like, most of it is just running through this notebook and then answering one more question. So that'll take you some time, but it shouldn't be a whole lot of time to spend on. So, and you can get started today in the next 20 minutes. And the link I just posted on the Discord channel. If it's not working from the lectures page, you can go through it. But I'll just quickly go through it, right? So this is fine-tuning with zero shot and also few shot prompting. Oh, it's not there, right? That's a good call out. Okay, so yeah, so we're looking at this notebook with zero shot and few shot prompting. So you have some setup here to set up your drive, and we'll also, so we're using a Llama 3 model, and we're piping it through Hugging Face. So you want to set up your Hugging Face token for authorization. So you go to your Hugging Face page, extract the token, and then when you run this command, it'll authorize you to log in, and then you can access the models from Hugging Face, specifically, let's say Llama 3 model. So let's say we're using Meta Llama 3.2, 3 billion instruct. So that's a 3 billion model that's already instruction fine-tuned, but you're fine-tuning it further through LoRa for a specific use case that we're looking at here, right? So this is loading that. There's some zero shot prompting. Without LoRa fine-tuning, you want to make a prediction zero shot evaluation. You can do that. The prompt is set up like this. Let's say you're looking at a buyer intent classification model, trying to classify the buyer intent, and these are the possible intents. And then, given a query, can you identify what the intent is? So that's zero shot. Same thing for few shot, except you have a few examples here for few shot, and then it makes predictions. And there are some queries. So maybe I should share a link to the data set as well, because you guys probably don't have it. I'll do that on the Discord. So then you have queries like this, some of which are genuine, some of which are not, some of which have some like things that ask you to reveal some private information. And so you want to basically take each of these queries and say, is it a query on product details? Is it on condition? Is it on availability? Is it an irrelevant intent? Is it some prompt attack that's happening? Is it offensive intent? So just identifying the intent. We're not responding to it. We're just identifying what the intent is behind the query. So for example, if you have something like this, it says it's prompt injection, and so on, right? So this is, and then if you did few shot evaluation, the same thing. So this is giving you different intents here. And then there is a data set I'll share. This is the data set that you want to look at. You can ignore this one here for now. So we'll just look at this data set, buyer intent data set final.csv. So I'll share that on Discord. You can take a look, load the data set, look at the intents. Let's skip to, yeah, and you can get results on the evaluation data set that's part of this. With no fine tuning, what's the evaluation? And you do the evaluation, you get some results here. Let's say the overall accuracy is 39% for zero shot. And then with few shot, it probably is a little bit higher, 53%. And then now I'm going to LoRa fine tune it on this data set and see what the evaluation result looks like. Does it increase? And what changes happen? So yeah, so you need to just basically make sure the data set is properly tokenized, and also the prompt that you want to use as part of your training data set, you want to include that here. So you go through training, then go through, this is evaluation. Let's look at what we got here. Yeah, so we got, with zero shot fine tuning, LoRa fine tuning, we didn't get a big bump here, but with few shot, we're able to get to 93%, which is very interesting. So if you looked at the few shot without fine tuning, it was 53%, and now we're at 93%. So you can see the bump that's happening from LoRa fine tuning. So your coding exercise, which you not expected that you completed today because we don't have so much time, but maybe you can set it up, get started, make sure everything's in place, and you can run a few of these cells, and then you can finish it by end of tomorrow. We'll go till maybe 6:20, and then 6:20 we'll have a presentation till 6:30. We only have one presentation today. So you can go until 6:20 and work on this. The notebook is on the Discord. I'll add a link to the data set so you can also access that.